You've talked about gravity, and I know that you're working on trying to defeat gravity. You're very anti-gravity. I'm very anti-gravity myself. I think a lot of our viewers
said that. I love the way you said that. I am very anti-gravity. I would agree with that statement completely.
Hey, everybody, tune in to Recent Targaryens.
Recent Targaryens. Recent Targaryens.
Yes, you got them, dude. Those things rock. I have to get myself some of those, man. They're totally RoboCop.
Friends, Romans, transhumanists, men, women, and everything in between. Introducing one of the most brilliant inventors, engineers, and alchemists in the world today, Jeremiah, the engineer. How you doing, Jeremiah?
I'm doing fantastic, and thanks for the wonderful intro, Andreas. It's great to see you too. I dare call myself a alchemist because, unfortunately, I know far too many alchemists, and by unfortunately, I mean unfortunately for those powers that be, because they would not like what we're doing.
Yeah, I think the words have been, used by whomever. I noticed you're wearing a fantastic pair of lenses over your eyes right now.
We've got lots of other options if we want to see infrared. We've got these guys, which block out all frequencies except for infrared, which means staring into the sun with these will pretty much blind you. And let's see, we've got these guys, which are specifically designed to block out blue laser wavelength light. They are yellow dichromatic filters, and they'll protect my eyes from the super high power 7-watt burning lasers that I've got a whole collection of, and I'm not even going to bother pulling out the other 6 pairs up there.
I do like, I have a pair of the yellow for lasers, and I wear them around the house a lot. It's just easier on the eyes, I think, just wearing the yellow glasses a lot. But yeah, having a visor, I feel like I'm protected by a lot. Everyone wants this thing going on. It's really all about this.
Cool, man. You got the whole chromograph right across your eyes.
Right.
Now, I don't know what they look like, staring through them, but they certainly look cool from the front side.
Oh, they're pretty good. I wonder if you can see.
Looking through them, too, you totally get a spectral split on those. The only thing cooler would be the dichromatic filters, and I'm sure you've heard of chroma depth glasses, which look like they're totally clear. But, man, I'll tell you, if you've got some nice graphics going on or you have a projected light image, they will turn your flat wall into a 3-dimensional environment unlike any other.
Right. Lenses and power density, something that people don't really just get excited enough about power density. Someone asked us, though, because I have the dailies now on the Xirtus channel where I'm doing all my videos on, whatever people are interested in about tachyons. And I thought maybe if I was going to do a video on tachyons, it would be ridiculous not to include you in the conversation. So I figured maybe you should just take it away. What do you think? What are tachyons again? Things moving faster than the speed of light. Is that possible? Is that all a bunch of hullabaloo? I mean, I want to hear what you have to say, really.
It's definitely not a bunch of hullabaloo. But again, I got to start off by saying 2 things. 1, I do not claim to be any kind of an expert on tachyons. And 2, we have quite a bit of evidence in the form of multiple papers produced by reputable companies and individuals showing the existence of superluminal transmissions in a variety of forms, not just photons. And we do have papers on superluminal photons, but superluminal electric transmissions, superluminal radio transmissions. So basically a tachyon is kind of a funny thing because it doesn't refer to just a single particle. A tachyon is a class of particles that includes tachyons, neutrinos, and what they call tachyneutrinos. And so the funny thing about a faster than light particle is if it crosses us, we won't see it until after its light speed bubble happens to strike us. And when it does strike us, the animation that we're looking at on screen right now is a scientist's rendition, a graphical representation of what we might see, where we see one particle traveling to the right and an information horizon or a bubble traveling to the left. And we sort of get this bi-refringement pattern because after all, it's flown past us long before we ever know that it's gone. Being struck directly with a tachyon head on, though, that would be an entirely different story. And tachyons are also interesting for a different reason, particularly not the neutrino brand of tachyons, because those can have apparently any arbitrary velocity. We already know that they'll go most of the way through the planet. For example, some neutrinos will pass right through one side of the Earth, down through the other. They'll go through all that dirt, all that mass, all that magma, and not touch a single particle along the way, not be slowed down or diverted at all. Yet, just every so often, one of them will strike the nucleus exactly dead on at exactly the right place. And so the only way that we can really accurately detect and look for these things is by burying chambers of water deep, deep underground, and hoping that we get a bombardment of one of these particles with a nuclei. And when it does hit, the nuclei breaks apart, produces a little bit of photonic radiation, and we pick it up with detectors, photonic detectors inside the chamber that line the walls. Otherwise, we still aren't actually sure if tachyons exist. Now, in terms of superluminal transmission, meaning something that travels faster than light, there's a common misconception that it would break causality. It would allow us to communicate backwards in time. And that's not really quite true either. If we have two objects, say, object one, me, object two, you, and I want to send a signal to you. If I send a signal to you in the form of a photonic emission, so I point a laser pointer at you, it's going to travel at velocity c, about 300,000 kilometers per second. But if I send a tachyon at you, because they can have an arbitrary velocity, and the faster they're going, theoretically, the less energy they have, it could get to you almost instantly. Does that mean that you've received information that would break causality? Of course not. That doesn't make any sense. But for some reason, there's this misconception that it would allow us to communicate backwards in time because it can travel superluminal. Well, an instant communication between point A and point B does not violate causality because you still aren't actually getting that signal before it was sent. You're just getting that signal before light arrived.
Right. Okay. So this is an interesting point I want to maybe go a little deeper into. So what do you believe is happening when, quote, light arrives? Right. So what is the process here? And what else is involved besides just waves?
We've got to accept that light is a special condition for electromagnetic radiation. In order for something to be a photon, it has to have a property of an electric wave that's facing in one direction and a magnetic field facing in the other. These two have to have a phase relationship of 90 degrees in order to really transmit and be a photon. Now, if they have a phase angle relationship that's not quite 90 degrees, they do really funny things. And we've been able to make particles like photons, for example, that have actual mass and travel slower than light. Now, light's not supposed to have any mass. It's just supposed to be the transmission of an electrical signal, or I should say an electromagnetic signal, from one point to the other. And so if I say, take an electron and I move it really quickly and then move it back, it's going to produce a little sinusoidal push, a compression in space-time that has a negative electric potential in the direction that I pushed it. And if I pull it back then to this point where it started, it's going to have a positive electric potential. So it's going to create a sine wave. That sine wave is going to travel in a transverse mode, meaning that it's not going to actually be, it's not going to move like a boat through the water traveling in a straight direction. What it's more going to be like is a ripple in a rope if I swing a rope up and down. Those transverse waves are limited to the velocity c, or the speed of light, because they're not actually traveling through space. They're just a fluctuation up and down from one point in space, and they are fixed because they don't carry any extra energy with them. They're limited in their energy density to the transmission of their signal. But there's a different kind of wave other than a light wave, and we call that a longitudinal wave, or a longitudinal transmission. This is where it's not transverse. It's not an up and down fluctuation. It's a back and forth fluctuation. This is what we would consider as a sound wave. Sound waves are longitudinal waves. But of course, sound waves are the physical impact of tiny little particles, in our case, particles of atmospheric gases that impact each other and transfer their momentum, just like pool balls basically striking one another and moving along, or like Newton's cradle, where you take one ball at the end, you let it go, and it swings, and it hits a series of other spheres that are just sitting there, and they don't seem to move at all, but yet the sphere on the other side instantaneously bumps off and swings in the other direction. So that will be an example of a longitudinal wave. Non-longitudinal waves don't obey the qualifications for photonic transmission. Yet, if we take a spherical object or a flat plate or literally any metallic conductor and we suddenly apply an electrical charge to it, like say a static shock from walking across the carpet, and we just shock it with our fingertip and a little spark jumps to the door handle, for example, that door handle becomes instantly charged. And once that happens, it will now emit a longitudinal wave. It'll travel out semi-spherically, depending on the shape of the object, and it's not limited to the velocity c, although its transverse mode photonic emission is limited to the velocity c. Eric Dollard and a variety of others have tried to tackle this problem because we've noticed that under certain conditions, signals seem to appear far before they should, before light can actually reach from point A to point B. And this is a major problem for physicists today, because currently it's considered that the speed of light is an absolute speed limit in the universe, and you can't actually transmit energy or information or power or anything else of the sort faster than light. But we know that can't be true because there's just a mountain of evidence that now is speaking against the idea that the speed of light must be somehow an information horizon limit.
And looking at some of these examples, the Alcubierre drive, the warp drive ideas, these all rely on this idea of wave versus particle. What do you decide is the most important thing, or how do we decide what do we deal with when we deal with wave particle duality?
I think wave particle duality is again a very misunderstood phenomena because we try to make everything in our particle physics universe view turn into this tiny little point source, infinitely small and quantifiable object. We want to treat things like they physically exist as solid objects, somehow ineffable and unchallengeable. But I don't really think that it works that way. In my personal view, an electron is not a physical, solid point source object. It's actually a wave function, and it has a three-dimensional power distribution that is not at all like the sphere. There's a lot of evidence pointing towards the shape of an electron being toroidal in nature, and there's some evidence of a slightly distorted semi-torus. But I don't think that there is actually a mountain of information supporting a spherical distribution. So if it is a wave, that means that the wave can pass through two individual slots and interfere with itself. And if we assume starting from the very beginning that it has a wave function that has a center, but it actually has a surrounding field, it's a whole huge field that has a point in that field where you could say, well, it's the strongest in the center, but it actually carries a very large amount of information in a very large area. Well, suddenly wave particle duality makes a lot more sense. Now we can understand how a single object that we call an electron is no longer a single object and it's a wave, and it can interact with itself because of that.
Okay, so that seems way more important. I think, okay, well, I think that's important because a lot of people on the internet right now are talking about this idea. Does light travel at all? You know, is light really traveling? Can you ever step in the same river twice? Is I think a very similar question, because you have this idea that maybe light is producing electricity. It could be that new light is being formed along the perturbations of what we're calling waves. How do we describe that then? Is that the same idea? Is it still light? Is it still light that's moving? Or are we tracking a change in particles that are exploding and producing new photons?
When we refer to light, what we're actually talking about is tracking a change, and I don't want to get all too technical to, swamp the audience and disinterest anybody, but what we're really talking about is a change in the permeativity and the permeability of free space. So what that means is space is sort of like, oh geez, do I want to use the word inductor? That might also be outside. I'm not gonna make an analogy here. Okay, so imagine that we've got a balloon and we can squeeze it in one direction or we can stretch it in another. This might be a good way to look at it. If we take a balloon, a spherical object, and we squeeze it in from the sides, it's gonna have to expand along the other direction, right? That's basically what we're looking at in light. We're taking some electric field and we're causing it to move from position from point A to point B and back again, or we're causing it to just move from point A to point B and it does not move back again. That's a special condition, which again can violate the first and second law of thermodynamics, and that's a whole special condition that no physicist is going to want to talk about when we have just a single directional or asymmetric force. But that would be our planet, for example, where we have a constant positive charge in the ionosphere drifting down towards the negatively charged electron well of the Earth, being continuously powered and continuously increased by solar impact of positively charged particles produced by our own sun. And it's, again, a longitudinal mode transmission because we live on a spherical capacitor, one terminal of which is the ground and the other terminal of which is the ionosphere. And we already know the source of the other charges. It's coming straight out of the sun. So what we're really talking about is a whip and a rope. We're talking about an up and down motion that changes the amount of energy space-time can store and moves along as an up and down motion. It doesn't move forwards and backwards. Again, it moves up and down. So light is very much unlike sound. It's, in fact, 90 degrees. It's quite the opposite of sound. But if we consider that there could be an electrical signal that can travel through space-time in the same way that a sound wave travels through atmospheric gases or any kind of a medium, now we're talking about a totally different condition that we can't really call light anymore. And we can't really call it a photon either. It doesn't also have to obey the rules of superposition because it doesn't go here to the laws of causality, and it no longer falls under those same principles, which are necessary prerequisites, special conditions for a speed limit.
Can you elaborate on the complementary opposition of sound and light waves and how they are similar and different?
I think a good example here. Well, besides the rope analogy, where you just if you stretch a rope real tight, and I hate to use this example because it's been used 1,000 times, but maybe not for this audience. If you take your rope and one person's holding one end and another person's holding the other end, if you give that rope a tug on one end, the person on the opposite side is going to feel that tug almost instantaneously. Now, of course, the rope is a physical example, so the physicist will say, well, it's going to take the speed of light for the tug to go from one end to the other, and that's correct. But if we're looking at that rope as a representation of physical space-time, and there's no real object there to accelerate, then again, we don't have a physical mass that's got to transfer from one side to the other. But if the same configuration exists where one person is holding one side of the rope and the other person is holding the other, and instead of pulling on it, we just simply move our hand up and down, we're going to create a transverse wave, and that's light. If it does not follow a transverse form, meaning if it's not an up and down or left and right motion, if it's a forwards backwards motion, it's not light, and it doesn't fall under the limitations of light.
So why is it that light travels faster? Why does electromagnetic radiation travel faster than sonic radiation? Why is sound slower?
Because sound requires the physical motion of massive particles, and particles have acceleration in physical mass, which means that they can only move as fast as their already present motion. So here's something interesting that most of us don't think about. The actual velocity of every single air molecule that we're looking through right now, which appear transparent, and that we're breathing in, they're traveling around 700 to 1,000 miles an hour right now. Every single little atom, every single molecule floating around that's right in front of us that we can't see, they're traveling between 700 to 1,000 miles an hour. In some cases, depending on the pressure and temperature, they're traveling even faster. So when we create a fluctuation or suddenly compress a bunch of those, it's their already present velocity that allows the sound wave to transfer through. Now, if we talk about a solid material, like say an iron bar or a guitar string, now those particles are already in a tensioned relationship with each other. So the velocity of a sound wave through an iron bar is much, much faster than it is through air. And the same thing goes for water, because water is far less compressible than air. The velocity of a sound wave or a longitudinal wave through water is much, much faster than it is in air. Well,
Okay,
go ahead.
No, sorry, continue.
Well, if we consider air as an analogy of vacuum conditions or our normal space-time conditions, where the electric fields and the magnetic fields, no matter which direction we look, right, left, up, down, forward, backwards, are the same in any direction. If they're just symmetrical and even everywhere, and we make a little change here, we can expect that that change is going to travel outwards away from the point where we made the change at the velocity of light. But if they are not the same everywhere, if, say, there's a lot more of an electric potential somewhere 5 feet in front of us, and I produce an electric field or an electric wave that's traveling from me through this area where there's a lot more electric field 5 feet in front of me, when that electric wave hits the electric field 5 feet in front of me, it no longer is going to be traveling through the same permeativity of space-time, meaning there's already some electric field there. And if we consider a balloon as being, generally round, trying to take its own shape, and we compress it, it's going to take a lot less force if we squeeze it in from the sides than if it's already partially squeezed and we try to squeeze it even more. So that electric field existing in that space, in that place 5 foot in front of us, that's already squeezing space-time, which means that there's pressure there, on electric pressure, and as the electric field that we create travels through that little spot where there's already an electric field existing, it's not necessarily going to travel at the same arbitrary velocity that it's traveling through, say, normal flat space-time where everything is even in all directions.
So what I wonder, I'm sorry if I'm
Go ahead.
missing it, but from what you just said, it sounds like a big reason is that light, or rather that sound, is traveling on material. And so we look at the difference of sound in water, and I wonder then how this relates to the idea that in immaterial vacuumous space, no one can hear you scream. Is that mean to say that sound isn't able to travel in a vacuum itself, or that it's unable to be heard until it reaches a literally particular destination? And then it made me wonder more about corpuscles, this idea of the atomistic view of light. So I wonder if you think that there's any correlation there. Is light activating or exciting a particle or subatomic particle in a way that we're thinking sound is interacting with matter in general as well?
That called corpuscularianism? Is that how
Correct.
you? Wow, that's
Big
a
words
mouthful.
back in the 1600s, but the idea was, I think Newton said that light had particles, and that the different colors were different particular size density, rather than they were activated particles, which is the way we kind of look at it now, is that we excite particles, and particles then behave ways because they've been excited. Not that these are migratory particles that have gone all the way across the universe. No, it's more that no, they have a suntan, right? So this is an interesting change, because at one point it was very, part of all of philosophy and also science to believe that light had a wave duality, that it was particular.
Well, if we go back to the analogy of how we can get a superluminal transmission of light through some amount of space, I hate to mention relativity because I have my issues with it, but I also have quite a bit of love for relativity, because relativity has really offered a very engineerable way and a practical way to visualize and conceptualize how we can use space-time to our own advantage. And one of the reasons for that is it has this variable condition called the metric tensor. Now, the metric tensor basically says space-time is compressible, sort of like a hydraulic. It's like a hydraulic fluid in a way, and if we try to squeeze it in from one direction, it's got to be expanded out on another. So we can't really truly compress it, but we can physically change which direction it's experiencing stress. And if we can modify the direction in which it's already experiencing stress, we can create special conditions in which we can transmit a signal through that space-time, even if we consider it to be an empty vacuum, a non-particle vacuum, and we can get what appears to us as a stationary observer to be a superluminal transmission. Like, for example, if we say the speed of light on Earth is 300,000 meters per second, and then we go out into space and we found that it's a little bit faster, well, wouldn't that mean that light's traveling faster than light in space? No, because what we do is we have this thing called gauge theory. So we like to gauge out or take whatever the speed of light happens to be in any given spot where we're measuring it, and we like to say, well, that's just simply the way it is, and this is an absolute. We call it the cosmological background, or the cosmological constant. It's also known as the gravitational constant. And that thing is a variable that we can actually change with technology. It's not recognized normally as being changeable or variable because the energy levels are calculated out to be ridiculous, but they're not. They're not at all. The phase relationship is the only quandary there. They are ridiculous energy levels if they exist at 90 degrees. But to the answer of your question, can you hear somebody scream in space? The answer is no, because it requires the physical compression of particles to hit each other and transfer their momentum from one particle to the next, just like billiard balls on a pool table. So if you take all the billiard balls off the pool table and you just simply take your stick and you swing it at nothing, the question is, what's it going to hit?
Wait, does it travel? Can it travel until it hits something, or does it not? Does the wave itself lose momentum without particles to excite?
Well, if you took one billiard ball and you threw it through space, like say if I took some particles and I was in my spaceship and your spaceship was, say a mile away, and I flung these particles from my spaceship to your spaceship, and there was just a certain number of these particles and they were traveling at a certain speed, when the particles from my spaceship to your spaceship, they'd be traveling through the vacuum, you wouldn't hear any sound until those particles hit your spaceship. And then you would hear the sound of those particles transferring their momentum into the hull of your spacecraft. And because I'm assuming your spacecraft is filled with some kind of atmospheric gas that you can breathe, then you're going to hear that sound. But unless I actually send some physical particles from me to you, you will not hear any sound in space because there's nothing to transfer the kinetic energy from particle to particle. But I can do something different. I can send you an electromagnetic signal which doesn't require the transmission of any physical particles at all. I can just produce an electric field, and you can receive that without any physical matter going from me to you.
Man,
That's why you can still hear radio in space.
So then it brings me back to this idea then about light being exciting subatomic particles. If then does that mean that light itself might not be traveling? If light itself is just exciting particles along the way, or are we convinced that there's, maybe this is a moment to bring up Michelson-Morley, because something that's important is, do we really believe in a vacuumous space that has no matter or ether or anything at all? What do you think about ether and Michelson-Morley?
I have quite a few things to say on the Michelson-Morley experiment and the existence of ether itself. I've studied the works of Tesla since I've been a little kid, and now going on some over 26 years studying the works of Tesla. My first coil that I was playing around with at 11 years old, and then 13 years old when I built a really big one, and that's when I started the gravitational research. I've been doing it for quite a while, and my opinion on the original Michelson-Morley experiment was it was foolish and it was done poorly. And the real reason why Michelson-Morley and the experiment got such a bad rep is because they did something that no good scientist should do. They made a claim before doing the experiment because they were so confident they were going to get the results to prove that there was a drift in the aether, that when they published their results and there turned out not to be, no one would listen to them afterwards. They did a series of other experiments where they actually had detected things. They changed the altitude of their detection equipment, and they changed the angle of their detection equipment. But in the very first experiment, it was parallel with the ground. And that's the problem. If we wanted to detect an aether drift, we have to put that entire laser table at an angle to the ground. So there was a new Michelson-Morley experiment that was done recently. Can't remember the guy's name that did it, unfortunately. But
I
what
might
they
be
did
able
is
to find it at the bottom of this. Hold on, let me go down. When was it done? You think the 90s or 80s?
Geez, that's a good question. When was the first Michelson-Morley experiment done?
The
I actually
Tremor
don't
test
remember.
73. Wolf did some tests in 2003. That might have been the newer test you're talking about. Herman Eisel. Here's the most
no,
recent
there's
test.
actually there's a newer test, and I highly doubt it's going to show up on this page because one of those things that came out through sort of the fringe community. But what they had done is taken the Michelson-Morley interferometer, and I replicated this experiment too. I built several laser interferometers, small ones, and instead of having them be parallel with the ground, all we did is we took the entire table and we stuck it on its side, so that when it rotates, one side is facing toward the sky and one side is facing towards the ground, and it just rotates around like that. So it constantly changes between the point that's facing towards the sky and the point that's facing towards the ground, instead of always being parallel with the ground and equidistant between the sky and the ground. What they found in that experiment was the gravitational field of the Earth would in fact cause a change in the fringe pattern, and it was very observable. 6 fringe changes or more for a tiny little 1 foot by 1 foot total path distance laser table, which is quite significant, showing that the gravitational field does indeed cause a drift in the velocity c, even over that tiny little distance. But this is one of those things that we should have been able to predict and not easily know, because we know that the time it takes for light to travel at our feet is slightly different than the time it takes for light to travel at our heads. Just standing upright, I mean, technically, we're thinking faster than the speed of light at our feet, which is kind of funny, but it's true. This is just the way gravitational fields work. The closer you are to the mass, the slower the time flows. And that's because mass is constantly emitting electromagnetic fields. And those electromagnetic fields have energy, and that energy has a mass equivalence, and that mass controls the local velocity of light. So the less mass you have around you, the faster the light goes. If you could remove all the mass completely, turns out light can appear to a stationary observer near a body of mass to be much faster than 300,000 kilometers per second.
Okay, so that gets us into some other things, because you've talked about gravity, and I know that you're working on trying to defeat gravity. You're very anti-gravity. I'm very anti-gravity myself. I think a lot of our viewers
said that. I love the way you said that.
You know, some people try to
I am
defeat
very
death.
anti-gravity. I would agree with that statement completely.
You know, and I think that's good. I think we all ought to be. And there's a lot of problems. There's a lot of problems with the word gravity even. Let's go to the etymology, and you can see that it has to do with weight or heaviness. And I want to ask you, because gravitum, it also, if you get down to the Latin root, has a lot to do with stoicism. I want to ask you, what do you think about the word itself and the definition in terms of weight or heaviness? Do you think that that really applies to what we're talking about, or do we need to redefine weight itself and heaviness itself, or how lost are we in this? Can we do anything? Are we going to be okay?
I think if we go all the way back to the Latin, and we're just simply going to say how much something weighs wherever we are, that's going to be our measurement of gravity. We're okay. But when we start to try and ascribe all kinds of properties and conditions to gravity and say that it's absolutely one thing or absolutely another, there we're crossing a boundary that we can't quite explain. Hence why we've just simply dubbed gravity as a fundamental force. Well, got bad news for a lot of people out there that want to really fixate on the idea that gravity is some kind of ineffable concept. It is not a fundamental force.
Sorry. Yeah, that's the thing. But how about buoyancy? Is buoyancy a real thing? Can we work with buoyancy? And
buoyancy is absolutely a real thing. Has anybody ever seen a boat floating on water?
Can buoyancy tell us?
Has anybody ever
gravity?
seen a helium balloon floating in air? Has anybody ever been around somebody full of hot air and felt a little bit pushed out of the room? No,
there's not a lot of anti-buoyancies out there. That's good. No anti-buoyancy.
No, buoyancy and the gravitational force are very, very different things, and they're certainly not capable of fulfilling each other's conditions. We can produce gravitational fields, and even though technically that's a Star Trek thing or more of a sci-fi thing, we're not supposed to be able to produce gravitational fields. It is in fact possible to produce a gravitational field, and one way that we can do it is simply by spinning an object. If we spin something, what we've taken is its inertia along a certain plane, and we have taken it and tilted it now and quantified it down to a rotational plane. So now it has angular momentum, and it no longer responds the same along the same axes. So for example, if you have a ball and you drop that ball from 4 feet above the ground, it will fall to the ground in the amount of time it takes for 9.6 meters per second acceleration per second to fall to the ground. But if that ball is traveling, and not just due to the curvature of the Earth, even if we compensate for that, it will take longer to fall to the ground if, say, we rotate or have a spinning ball. In fact, if it's a spinning gyroscope, even more so, the faster we spin a gyroscope, but we fling it along and propel it, it will not fall to the ground at the same rate as a non-spinning gyroscope, or just the same exact object that doesn't have angular momentum. And that is a violation of what we would conventionally consider to be an absolute fact about how mass responds in a gravitational field. It turns out that adding spin changes the way an object responds to gravity, which tells us as scientists that gravity must somehow be interacting with every single particle within that material in such a way that it matters whether or not a field produced by that particle that reflects down to the body of mass and then comes back to pull on it actually matters. Because the thing is, if I have an object that starts out in position A and it's constantly emitting a field, and its field has to now hit some object at position B, let's say the Earth, and then the Earth has to then send back a field or reflect a field that hit the position of the object at position A, but the object is no longer in position A. If it's moved, meaning it has some kind of velocity, it's not going to be in the right position to totally receive its field, meaning that it won't be able to fully react in a Newtonian way because it's moving. And that creates a bit of a problem for saying that gravity is some kind of an absolute constant or an ineffable field or a universal fourth force. It means that it's somehow reliant on the inertial vectors of the object that it started with. And so if we can change those inertial vectors, we can also change the gravitational coupling coefficient and make an object weigh less, or if we want to, make an object weigh more.
Elaborate on that a bit more. And maybe, okay, so just also to explain the differences, we're looking at this picture and it talks about density and buoyancy. And the way density and buoyancy works is that the object has to be proportionally the same mass, and it displaces a certain amount of mass. If it's lighter, then it will rise. And so it has to do with this, again, this idea of weight. But you're telling us that with the mass of an object, somehow we can change the weight. But how is that possible?
Right, we can change the weight without changing the buoyancy.
Okay. And so how does that work? How do we change the weight?
We have to modify the inertial vectors that are in that object. And without getting too technical, basically we have to add some kind of momentum in a certain direction to that object that's not
moving.
along the same, that if it's accelerating, particularly if it's accelerating, we have a causality violation because there's a new factor introduced that we've only been recently looking at in quantum physics and in FTL drives, especially for the the sci-fi nuts working in particle accelerator laboratories. We now have to consider this idea of something called an information horizon or a Rindler horizon. And basically what this means is if an object is accelerating, certain amounts of information or light cannot ever reach or catch up to it along one direction because it's accelerating in one direction, whereas it's actually going to come into or impact light that already existed more so in the direction that it's moving or accelerating into. So the information horizon causes a violation in that uniformity, an asymmetry, if you will. And this allows us the possibility for metric engineering, meaning we can modify the way an object reacts to space-time itself. And if we can do that, we can modify the way an object reacts to gravity, which is just a property of the local space-time.
So maybe looking at this, for example, we have ferromagnetic nanoparticles that have been aligned on a triangle, maybe like a pool rack, and then it has the ability to change momentum based on the electricity that's changing which direction the polarity is flowing. So an electromagnetic lift. So is electromagnetism all that anti-gravity is, or am I downplaying it, or is there more to it?
I have two competing theories that are still running in my head, and I haven't got absolute evidence to support one or the other. But I do believe that gravitational coupling to an object is both an electrodynamic phenomena. I don't want to call it an electromagnetic phenomenon because electromagnetism refers to a 90-degree phase relationship and also falls under a variety of special condition equations that we know now as the Heaviside-Gibbs equations, which also are mixed in with our current models of general relativity and follow the Lorentz transform.
So you're saying magnetism is a form of spin state. It's really all spin state, but magnetism really is a relationship in spin state that you like. Okay.
Right. And more so, magnetism is just simply an electric field viewed from 90 degrees. Sort of in the same way that we talked about how a transverse wave is different than a longitudinal wave, where one is an up and down or a left and right motion, and the other one is just a back and forth motion. Well, those are totally different concepts when you consider how they physically compress space-time. And if we're looking at gravity the same way, and we say, well, the only way that a gravitational field can connect with an object requires it to become aligned with the gravitational body or the source of mass, in this case, if we suddenly change the angle that some subatomic particle or a series of subatomic particles or even a bulk of matter has to that mass, it no longer can experience the gravitational field the same way. Well, we can do that with spin states. So magnets themselves, they have an electric field around them that eventually reaches neutrality because they will absorb electric charges until they reach neutrality, and they do that almost instantly once they're made. So like a permanent magnet, when you make it, it needs to absorb a significant amount of positive potential, which in this case means it has to emit or radiate some amount of free valence electrons out into the environment in order to reach neutrality. Because when we take a solid object that's not magnetized, but it's made of magnetic material, and we magnetize it, it becomes negatively charged due to the fact that all the spins are aligned and their degrees of freedom become restricted. So it'll actually pick up a negative charge, and in order to reach a neutral charge to the environment, it's going to have to ionize or pick up some positive charges from the external environment, which means it has to give off electrons in order to do that. And so it'll usually have a cloud of positive ions around it, or it'll have a lack of electrons. However, if we make it in a vacuum and it doesn't have access to either electrons or ions, it'll just maintain that state of negative charge. So gravity is partially electromagnetic, but the reason I say it's electrodynamic is because it involves acceleration. Acceleration is so important. It's not just a constant motion. It's not something traveling at a fixed velocity. It means that something is traveling at a changing velocity constantly. It's always either accelerating and decelerating, but it's never stationary. If we want to experience gravity, we have to have that property of acceleration happening in order to couple with the gravitational field. And if we can change the amount of degrees of freedom that an object has to accelerate within, we change the way that it couples to a gravitational field.
So in terms of gravitational electromagnetism, are we saying then that we're polarized and that's creating magnetic fields, which are defining our resonance patterns? How are these set up, and are we able to manipulate them? Should we be worried about technology with radio? Are we interfering with our gravitational electro spin state magnetic system that we have?
That is an excellent question, Andreas. That's an excellent question. And it turns out the answer to that is yes. An ordinary radio transmitter like a walkie-talkie or a cell phone will literally produce a tiny fluctuation in the amount of gravitational field around that device, especially around the antenna where you're having the maximum velocity of particles accelerating and decelerating. In this case, those particles are electrons. Well, just by the fact that those electrons are traveling through the conductor, the antenna in this case, they create just a bit of a fluctuation of the local energy density surrounding that physical object being the conductor. And they do create a tiny variation in the gravitational field for the antenna.
Wow. So in a bigger scale, could we use this to control, could we use this as a system perhaps for travel, for free energy? What are some of the implications or possible uses of this kind of thing?
Could we use it for free energy? Well, without using those exact set of terms, could we use it to produce an extra output of energy or something like that? And the answer to that is also yes. If we consider metric engineering, basically modifying the variables of space-time itself and its response to an electromagnetic wave, if we add a bunch of electromagnetic energy into a small volume of space that we control, and we already have some current flowing through a wire, like say a solenoid or an electromagnet in that area, and we surround that solenoid or electromagnet with an extra field that's not produced by it, but is instead superimposed, now that solenoid or electromagnet can create a magnetic or electric field that's different than it would otherwise be if we hadn't superimposed a field. That means that we can basically make one electron have more than one electron of charge, or more than one electron's worth of electric field. Or we can make it have, as it would appear from an outside frame of reference, less. And since we're living on the biggest well of electrons mankind could ever imagine, the entire globe, if we could just simply change something in a local area, like Tesla wanted to do with the Wardenclyffe Tower, or any large transmitter that basically pumps energy into and out of the Earth, pumps electrons into and out of the Earth, now we can change the amount of energy density for electrons moving in an antenna. And that means for an outside frame of reference that's not exactly at that location, it may see the transmission signal of 100 watts as being much, much stronger than 100 watts, because by the time the energy sort of unravels itself and decompresses from what we call the near field around an antenna, past the Fresnel zone and into the far field, it will appear to have a significantly greater amount of energy due to the fact that it was compressed near the antenna and it got a chance to sort of decompress or breathe a little bit in the far field.
So one of the things that makes me think about, if you look at the Alcubierre Drive, we were talking about warp as a Star Trekian, use of some of this technology. There's been a few other converging ideas, including the Krasnikov tube, which is very similar to a warp drive, but it has a bit more to do with that idea of light in a vacuum, and when it finally hits a distance, but also that you can travel back to the beginning of when you first started to travel, I think is part of the deal, because it's a distortion of space-time that can allow you to appear right after the time they've left, right? So because no light is broken down, no particular degradation happens in a vacuum. So theoretically, everything should just be the same until it reaches its point, and you can be stored in light. And we've already proven you can store data in light. What's the difference? And then projecting a being or projecting an information through light. What do you think makes more sense? Do you think that we're looking more at bending light, or that we need to bend mass, or that we're exciting spin state? What's the best way to approach anti-gravity?
I guess it depends on how fast we want to move and how much time we have to set up the conditions required for creating the superluminal motion of physical matter. Because what we really care about with warp drives is we ourselves want to get on board some kind of a craft and actually go from point A to point B at a speed faster than light. And in order to accomplish something like that, there are two lovely possibilities that have been theorized out there. One of them, and one that I've looked into quite a bit, was, of course, the Alcubierre drive. I created plasma simulations, which I would love to have pictures of right now, but I don't because I'm on my cell phone and my computer is just choking at its RAM. And the other one would be the Musha jump drive. The jump drive is
how do you spell that? Musha jump drive? How do you spell that?
I think it's Musha. I think it's M-U-S-H-A. I better look that up myself. If you just type in jump drive, you'll find it. Yeah, it is M-U-S-H-A.
Let me see here. Musha jump drive.
So the jump drive is interesting because what it does is precondition the space between itself and the destination that it wants to go before it ever moves. But when it finally does move, the space-time has been stressed so strongly that the velocity through that space from outside from a reference appears to be nearly instantaneous. Yet for the occupants on board, basically they're not moving very far. They're just simply moving a couple of feet, say, or the full distance of the craft itself, because we've already put so much stress in the space that it can't take anymore. And any extra energy that we add into it at that point sort of snaps it. It's almost to say space-time has a limit of how much energy you can pump in. And if you exceed that limit, you can instantaneously transit from point A to point B. Whereas with the Alcubierre drive, we're continuously modifying a brand new amount of space-time in front of the craft and continuously returning the energy on the backside of that spacecraft. So one system is dynamic and can operate from the very beginning to the very end in a fairly linear way, and the other system requires us to set up the conditions ahead of time before we can actually make that superluminal travel, which means that, say, I can build it today, and maybe, you know, your great grandkids can get on board that craft and instantly go to Alpha Centauri because we've already created the field today.
The other thing I'm looking at is this idea of holographic universe, then holographic universe. And if you look at the holographic universe idea of density being projected on a single flat plane, what does that say about light itself or radio wave? What do you believe about density? Do you think that it's likely that we're living on a holographic plane, and is radio the way we're interacting on a holographic rainbow hologram? Is that
the reason I've never really liked the term holographic universe is because we look at holograms and holographs in our current understanding as some kind of a fixed or unchanging image. It's something that is locked in. And there's a partial truth to that. The physical pattern of electromagnetic and gravitational emissions from all physical bodies of matter that contain mass and are in motion, they do set up a geometric pattern of interactions for their fields. And we could say that's sort of like a hologram, but it's not quite like a hologram because it's continuously variable and dynamic. So does it create some kind of a fixed construct that we can absolutely tap into and unravel? In the way I see it, I don't think so. So I would look at it a little bit differently, and I don't quite think that holographic is the right way to describe it, though I guess as an analogy, it's probably one of the closest ways we can say there's a complex interaction of all these fields, and they really do have a three-dimensional structure. That three-dimensional structure is the physical three-dimensional structure that they're already packed into in their current state of existence. Meaning, say, a bismuth molecule being generally pentagonal, or a carbon matrix being generally hexagonal, or say something else that has a square type formation or a crystalline formation like a perovskite, for example. These things have fields that will also project outwards in that same shape. So for every piece of matter and every single individual particle interacting with every other particle, they really do have three-dimensional shapes that permeate outwards from their point of origin and create real physical fields in their exact image. But again, that is a type of field interaction that's constantly changing. So it's not physically locked in, and I don't really know of any way that we could unravel it or go back to some prior condition that it existed in. And
right?
that's
So what do you think about?
Stay away from holographic.
what do you think about entanglement then? Do you believe in entanglement, quantum entanglement, or particular entanglement?
Everything that I've seen on the description of entanglement, in my personal opinion, has been a misnomer, and I have read quite a few papers on entanglement. One of the most egregious misunderstandings is this idea that if we take a photon, a single photon, as we call it, which is actually just a transverse electromagnetic wave, and we pass it through a dichromatic 50-50 filter where half of the photon's energy goes straight through and the other half of the photon's energy gets diverted 90 degrees, that now these two photons, which are technically just the same electromagnetic wave having its energy divided in half, will now always be at the exact same phase no matter where they are. Well, in order for that to work, we have to also assume that they're traveling through a flat space-time, meaning that the electric and magnetic fields in the space they're traveling through are completely the same for the path of both those photons. But if they're even slightly different, the entanglement appears to fall apart. So all we've really done is we've synchronized two stopwatches, and this is the way I look at it. When we talk about quantum entanglement, it's more like synchronizing two different stopwatches. We can say this photon has a phase angle and it has a position, so the electric and the magnetic fields are related to each other and have a certain velocity. Well, if you have a stopwatch that you start in, let's say we have two stopwatches on the ISS out in space, and we send one of those stopwatches down to Earth. We know that no matter where we move the two stopwatches on the ISS, if they're absolutely precise and perfect, they will be always synchronized no matter what we do, as long as they move along the ISS parallel to the Earth. But what if we take one now and we move it slightly closer to the Earth or slightly farther from the Earth, they're going to suddenly become disentangled because, well, they're going to be experiencing a different amount of gravitational field. So the rate flow of time will be different. And the only way that we've tested this on a small scale with lasers, generally speaking, is that we're interacting one of these two photons, and we're going to be able to assume that the other one is in the same flat space-time. But it breaks down when we have a variable refractive index of space. So I would disagree with the general assumption of quantum entanglement and how it's explained.
That's awesome.
I
Actually,
don't think it works that way at all.
there's not enough people that really are questioning quantum entanglement, so I appreciate that you're taking that stance to at least question it. I think one of the things that bothers me about the slit experiment is just agitating a particle to do something. Yeah, it's going to have certain kinds of repercussions until you agitate it again, and then it's going to change. So that's something I think is something people miss on quantum entanglement, is that you're training something, and for a while it follows a trend until eventually something happens to it and it stops.
Yeah, exactly.
Let me also pull up an article I have. Well, a couple things on different kinds of theories of alternatives to gravity, induced or emergent gravity. Do you want to maybe elaborate on this idea of natural or inherent gravity versus induced or emergent gravity, and what the difference is?
Well, I'm not familiar with what's officially considered to be either or. I have not read that article on the induced gravity, so I'm not sure what it says.
Legit. I can let's just go over it anyway together then and see what you
let's
think
go
about
over it together, and then I can give some feedback perhaps.
Yeah. Sakharov observed that many condensed matter systems give rise to emergent phenomena that are analogous to general relativity. For example, crystal defects can look like curvature and torsion in an Einstein-Cartan spacetime. This allows one to create a theory of gravity with torsion from a world crystal model of spacetime in which the lattice spacing is of the order of Planck length. Sakharov's idea to start with an arbitrary background pseudo-Riemannian manifold. I don't know if you're familiar with pseudo-Riemannian, the differential pseudo-Riemannian differential manifold with a metric tensor that is everywhere non-degradable. Okay. In modern treatments, possibly with torsion, and introduce quantum fields, matter on it, but not introducing gravitational dynamics explicitly. This gives rise to an effective action, which to one loop order contains the Einstein-Hilbert action. I believe you're familiar with the Hilbert action, which is the first principle of action with the metric signature, whatever, with cosmological constant. In other words, general relativity arises as an emergent property of matter fields and does not put out put in by hand. On the other hand, such models typically predict huge cosmological constants. Some argue that the particular model proposed by Sakharov and others have been proven impossible by the Weinberg-Witten theorem, which we can also check out. However, models with emergent gravity are possible as long as other things such as space-time dimensions emerge together with gravity. Developments in ADS CFT correspondence after 1997 suggest that microphysical degrees of freedom in the induced gravity might be radically different, but the bulk space-time arises as an emergent phenomenon of the quantum degrees of freedom that are entangled and live in the boundaries of space-time. According to some prominent researchers in emergent gravity, such as Mark van Ramsdonk, space-time is built up of quantum entanglement. This implies that quantum entanglement is fundamental. Well, we kind of covered on how you feel about quantum entanglement. So that kind of answers that. But then this idea of Verlin being also for entropic gravity proposal and having to do with negative pressures, negative densities, things like that. And also the Weinberg-Witten theorem, which states that massless particles with spin J is greater than half cannot carry a Lorentz variation current, while massless particles with spin J greater than 1 cannot carry a Lorentz variant stress current. The theorem is usually interpreted to mean that the graviton J equals 2 cannot be a composite particle in a relativistic quantum field theory. So I don't know.
I think I would agree more with the Weinberg theorem because I do look at, well, I like the description emergent gravity. And the reason for why is I do look at gravity as an emergent phenomena resulting from the phased interactions of all the electric and magnetic vector potentials produced by the physical motion of all particles, including the neutral particles that we have producing a physical kinemassic, as the term has been coined previously by their inventors, a kinemassic field, which means that if we move some mass really, really quickly, it actually generates this sort of wake field behind it and a compression wave in front of it. So I think that gravity is, in fact, an emergent phenomena. And I agree with that, but I don't agree with a lot of the other theories that have tried to explain how we would get or calculate out unemergent gravity. I've done a series of experiments to try and synthesize a gravitational field, which have been pretty successful up to this point. And the simplest example that I'll give, which is one that almost anybody could replicate with some basic parts from a photocopier or one of those old school backlit TVs that have the fluorescent tubes in them, CCFL display TVs that have an LCD panel. I took a transformer from a CCFL monitor, I think it was a Dell monitor. I connected it to a ribbon cable that had 20 parallel ribbons, and every other ribbon was connected in parallel. And so I had one set of ribbons connected to one side of the transformer's output. It's about a 2,500 volt output native to the transformer, and the other set was connected to the opposite side. Well, if I take that same ribbon cable and I place it close when the high voltage of the transformer, 50,000 cycles per second, high voltage at about 2,500 volts is oscillating, I can pick up a small glass panel, I can pick up a small piece of metal, I can pick up foam beads, I can pull on an object, I can stick the entire device itself with its battery to the door, it'll stick, it'll attract anything. Doesn't matter what it is. It doesn't repel. It can't repel, but it will attract anything universally. And it's a hyperbolic curve. So it's not quite that parabolic inverse square curve that we would expect from a normal gravitational phenomena when we're talking about a mass field. It instead follows a hyperbolic field where the closer that you get to it, you get a much, much, much greater increase up to the point where you're physically touching the surface of it. But we've been able to simulate the same types of gravitational phenomena where we get a universal attraction and no repulsion by using electric fields. And then we go back to the work of Tesla, which talked a lot about dielectric field, which is one of those things not currently recognized in Maxwellian electrodynamics. And that's because it was gauged out with gauge theory, because the calculations were just too damn complicated for practical engineering. And that's where we ended up getting the Heaviside Gibbs adaptation of modern electrodynamics.
It seems though they like dielectric radiant fields are the spiral from coming at you, right? So instead of just looking at this up and down Egyptian hieroglyph, we're imagining, the actual three-dimensional momentum and travel in all directions of a wave. So what kind of formulas, what kind of work are we doing to understand dielectricity?
This is why it gets complicated. When we normally think about the degrees of freedom in space-time, we think right, left, forwards, backwards, up, down. But we also have another degree of freedom, which we don't often think about in physics, and that's twist or turn. That we call torsion. And that's represented by something called the torsion tensor. Now, the torsion tensor usually represents the magnetic field energy in a given volume of space. But if we say have some arbitrary volume of space, 1 meter cubed, and we have a twist inside of that 1 meter cubed, we can now change the amount of energy inside that same volume without creating a push or a pull or a up and down or a left and right motion. We can now actually increase the energy without having to create any kind of a linear effect. So the torsion tensor gives us the ability to increase the energy localized to a volume of space, and that means the space is going to appear from an outside observer to weigh something. It's a rather strange phenomenon to think, wait, space is heavy? Space has weight? The vacuum itself, the matterless vacuum that has no physical particles in it apparently has weight? Well, yes, it does. And we call that physical weight the gravitational constant, which is why we say, even out there in the deepest depths of space, there's still some kind of speed limit for a transverse wave created, stating the gravitational constant, aka the cosmological constant, just different ways to describe the same phenomena. And I think the way we can explain this gravitational constant is by saying that space has not necessarily a motion in any one of those 6 directions that we normally think of, but it has a twist inside of it that's much more twisted or much less twisted, depending on where you are, depending on the amount of stress energy in that region. And that means if we can create a twisting field of any sort, whether that be a twisting electric field, a twisting magnetic field, a twisting kinematic field, or any matter of speaking field that we can twist instead of pushing, pulling, stretching, compressing, or whatever, we can now create a brand new space-time constant that now has a physical mass equivalency. And of course, we know that mass is going to have gravity. So if we can create a synthetic mass, a virtual mass, we can create a synthetic gravity. And that's what my little experiment that I was describing with the ribbon cable simulates. It creates a synthetic gravity by increasing the electromagnetic energy in a very small volume of space.
Man, so in terms of modified Newtonian dynamics, then if you think that Newtonian dynamics are working with torsion instead of with ether or with some sort of another weight, it has to do with...
still do like ether. And
yeah, I mean, we'll go into that then. Elaborate, because it seems like the argument for torsion is against ether. It's saying, well, we don't need ether because we have torsion. Or am I missing some nuance?
There are many different views of ether throughout history because we try to describe this idea of a vacuous, matterless space in some kind of way, saying that, well, there must be some kind of a fluid-like thing, some kind of a corpuscle, some kind of substance out there that we just can't quite put our finger on and figure out what it is. Well, what if that corpuscle, what if that substance happened to be pairs of positive and negative charges that we call positrons and electrons? And what if, say, for example, we said that we never truly annihilate a positron and electron when they come together, but instead, when they do come together, they continuously try to reach each other, never quite truly reaching each other, but they become at such a high rotation speed that they create an information horizon around themselves where they're untouchable and their physical size shrinks down. The reason why we know that there's very large amounts of merit in researching that phenomena, that there could be physical, huge amounts of matter sitting in every single physical cubic centimeter of space, and why it would be a tremendous amount of energy is this. If we take a photon of 1022 kiloelectron volts, and that would be just, a photon that has the equivalent energy of 2 electrons, for example, and we just shoot it out from a cannon, from a photon cannon, in a straight direction, it will travel outwards, and at some point, strangely enough, we'll see a positron and an electron pop right out of the vacuum. The strange thing is, if they were literally everywhere, continuously permeating all space, it would happen right at the very edge of the emitter head, right at the tip of the laser, but it doesn't. Instead, that photon will travel some arbitrary distance, sometimes more, sometimes less, regardless of the fact that it has the same energy. And at some point, it seems to strike an invisible something, and then we get a positron and an electron that pop out of the vacuum. So the question is, why does the amount of time it takes for a photon with enough energy to separate a positron and an electron take any amount of time at all instead of simply producing a positron and an electron instantly. What that tells us is, there must have been a positron and an electron already paired up in that space, and it just happened to be in the right place when that photon hit it to separate them, so it must have already been there. Meaning, if it was already there, the positron and the electron never annihilated, they only recombined. So if we eliminate the word annihilation from our context and we instead replace it with the word recombination, now what we get is positron-electron separation and recombination instead of positron-electron generation and annihilation. And this completely changes the way that we have to look at space-time, because now we have to accept the possibility that we might be swimming in the sea of positron-electron pairs. If that's the case, we're surrounded by so much energy, we wouldn't even know what to do with it. And now we get into the ZPF, where we're talking about 1 coffee cup's worth of positron-electron pairs containing enough energy to boil the world's oceans. That's effectively what the ZPF refers to, and I think that's also explaining why we have all these wild fluctuations everywhere that we look. We have these constant electrodynamic fluctuations in every direction. Even at absolute zero, they still exist, hence 0-point energy in its term. We can cool something down and we can remove all the energy we want to, and we can block it all out, and we can remove all the matter, but we still have this energy, and it just seems to be there. My theory is, and the only thing that makes sense to me, these particles already have to be there, and they explain why a photon with a sufficient amount of energy to separate those two does not instantly cause them to separate from each other, and why it has to travel some arbitrary distance before they pop out. That could literally explain why we have a gravitational constant at all. It might mean that way out there in space, no matter where we look, we're literally swimming in a sea of positron-electron pairs.
If that's the case, then what does that say about, I mean, what does that say about the vacuum? Does it mean, in other words, it's not a vacuum, and our understanding of...
Exactly. It means it's not a vacuum at all. It means it's filled with actual matter that's already come into a state where it's got the smallest information horizon it possibly can, continuously chasing itself. And if we have sufficient electromagnetic energy, we can split it apart and use it, literally creating antimatter straight out of the vacuum, meaning we don't need a source of antimatter. We don't need to question where we're going to get it from. We can create it as we need it. And the beautiful thing about creating antimatter straight out of the vacuum is we get to choose where it recombines. So if we can separate it in front of our craft and we can recombine it at the back end of our craft, the recombination energy that it's going to give us back in the terms of photonic forces are going to be tremendous on the backside, pushing us forward and thrusting us through space, even up to superluminal velocities, because if it in fact is the speed of light, which is only limited by these positron-electron pairs that are out there, and if we can split them apart, that means we've changed the speed of light in front of our craft, and it's now much, much faster because nothing is in the way. And if we recombine them in the back, it now means that we're recombining them, creating more of this space-time compression behind our craft, so it's going to push us forward. That would allow us superluminal travel.
So, but these kinds of particles are, what kind of mass are we talking? I mean, you're saying essentially that this is similar mass to mass we're familiar with, because particles are becoming the same kinds of particles again as we're passing through, like water or oxygen, hydrogen, carbon. What kind of particles are we imagining this would be instead of a vacuum?
If we talk about, just say, an atom is going to have a proton, neutron, electron. These are the 3 constituent particles of normal matter. They're going to have any combination of these 3. We can have just a proton and just an electron, say, for example, hydrogen. But if we're talking about just the electrons, just those valence electric charges that we can't quite explain the shape or the behavior of, they seem to be fundamental elementary particles, and they don't seem to have any direct counterpart other than their oppositely charged pair, the positron, and they're sort of off and doing their own thing. Well, if we can control where those things pop in and pop out of space-time, we can literally modify the very fabric of space-time itself. That gives us total control over metric engineering and total control over the speed of light. So here we're just talking about electrons and positrons. And again, we can just consider electrons as being this very, very low mass, very high velocity, very tiny particle. But again, it's not quite a spherical particle. It seems to be more of a wave function. And I would also say the same applies for the positron, where we're looking at two different wave functions with spin properties that are opposite to each other, or reverse from each other.
How about ionized matter and plasma? What do you think about ionization of this non-vacuum? Then is there, how ionic is it in space? If we can call it that, because it seems like we're not allowed to use the word gravity or space now, because I mean, I guess everything is space. You know, there's a space in the back of my house, so there can be space that's non-vacuumous. But is it ionized?
I wouldn't call it ionized because it's neither missing or having an extra electron. So when we talk about something being ionized, what we're talking about is a nucleus that either has not enough electrons to balance out the number of protons it contains, or it has too many. So anything that has too many electrons or not enough electrons to equal the number of protons, that's ionized. That's why we don't consider just, say, free neutrons to be ions, because they don't have that charge, so we just call them neutrons, and they're their own thing. And neutrons can impact with kinetic motion other particles, and they can rip electrons off, or they can smash into a nuclei, and they can knock off protons or other neutrons, and sometimes they can even hit with enough energy to physically break apart a proton and create an electron and a neutron, or a variety of other interactions, and some extra photonic radiation on top of that. So ionized really just refers to electrons and how many it has in excess or not enough of in any given atom.
Do you think that the space carries a charge, or is it some sort of medium for the electromagnetic waves and ionized material, radiation, comets, whatever? Are these things supposed to be traveling through an inert medium, or is the medium itself charged by these things and carrying sometimes extra ions?
The medium itself is charged by these things. If we have a bunch of positive ions, they're going to have a lack of electrons, which means that the protons themselves are going to create a positively charged field that we would just call an electric scalar field. So that scalar potential is going to be positive in nature. If we just have a bunch of electrons and no protons, we're going to have a negative scalar potential. And now if we talk about scalars, we can physically charge a volume of space by placing these particles in that space, and from wherever the location those particles are sitting, outward from that location, we're going to have a bubble surrounding each particle. And if we have a whole bunch of them crammed together, we can get a really, really strong amount of electrostatic charge in that volume of space. So that means any charged particle is going to react quite differently when it tries to interact with that already existing electric bubble of charge.
So another thing mentioned was dark matter or antimatter even, and in modified Newtonian dynamics, Mordechai Milgram, an Israeli physicist, came up with a concept in modifying Newtonian second law so that the gravitational force came to vary inversely linearly with radius, as opposed to the inverse square of the radius as Newton's law of gravity had proposed. And so in doing so, and changing this slightly so that the inversely linearly with the radius exponent of entropy is changed, there's a lot less there's an extremely smaller number of accelerations or density issues, and it almost calls into question if dark matter is necessary to exist. And that's a big reason why we hope it does, right? Unless we're interacting with it. So are we interacting with dark matter? Does it exist? Are we measuring it wrong, to say the least? What about dark matter?
Dark matter is a bit of a tricky one, but I will touch on dark energy. Okay. I suppose you call a positron-electron pair in a constant state of self-chase. As far as my theory goes, I suppose you call that itself dark matter, and you can compress the amount of that stuff in a volume of space. So if we have a lot more of it, it may act like the physical amount of matter. But dark energy would basically be the equivalent of that in electromagnetic form. So as we mentioned much earlier in the show, an antenna that's transmitting power, electromagnetic power, is going to have a slightly slower velocity of light around itself. So it will create a compressed field in what we call the near field of that antenna. As far as I see it, that's what we are looking at when we're looking at astrological deep space events that appear to have different velocities of light, and they seem to have redshifts as the light travels out of those volumes of space. I think that the electromagnetic energy density explains why we look at so much redshifting going on, whereas dark matter would refer to the physical matter counterparts being the positron electron pairs. So in my opinion, I think dark energy is just referring to a volume of space that has lots and lots of electromagnetic energy density crammed into a very small volume of space.
So do you think then does dark fluid, which dark fluid seems to tie together the two concepts, do you think that dark fluid is a correct analogy, or is the dark fluid taking away from the credit that is dark energy, which is really the primordial controller here or motivator?
I don't think that we can really ignore either or. I would say that calling it dark fluid is just as bad as gauge theory, because we've taken two individual things, each of which are modifiable on their own, and we've tried to cram them into one simple word to make things easier to understand. But right. I think by doing that, we've removed our ability to engineer. And that's why I would stay away from that and keep dark energy and dark matter as their own thing and work with them independently, where we consider dark energy to be electromagnetic energy density that's compressed within the space-time tensor. Space-time tensor. So this would be that metric tensor that we were talking about engineering with electromagnetic energy, and we would consider dark matter to be simply these positron-electron pairs and how many of them are in any given volume of space from some arbitrary frame of reference that we choose.
So do you think dark matter is prevalent in the sense that, you know, you look at almost anything and there's a negative flow of ions? Do you think the natural state is dark and I think it's looking to be filled? Or how do you think that the relationship goes between dark energy and, do you even call it regular energy? What do you call it then? Light energy seems wrong.
I think regular energy, aka normal light, only exists in what we would consider to be the far field of any radiation structure. So when we get really, really close to matter, we're not looking at the same kind of refractive index of space-time that we're looking at when we get far away from that matter, meaning that the rules don't quite work the same way if we get down onto that quantum scale, on the subatomic scale, in that space between the valence band and the physical nuclei of an atom itself. In that space between those two, we're looking at a very different set of properties in that space-time than we're looking at outside of that in the far field. And if we can consider synthesizing something like, say, an atom on a very large scale where we have the same type of positive and negative charge, or some kind of a dipole moment that's rotating really, really quickly, we can now engineer a synthetic bit of matter that has real tangible mass that we could measure on a scale, and it would change the weight of something placed above it or near.
It's incredible.
Yeah, you're pulling up the right diagrams. Yeah, so if we get really, really close and we get in the far field, it just doesn't act the same. We can actually get very large amounts of electromagnetic energy into a volume of space that seems way too small to hold it. And as the energy leaves that region, it will redshift out. It will seem to lose energy as it reaches a 90-degree phase relationship between the electric and the magnetic field. But in that very close field to the antenna, the electric and magnetic fields are not at 90 degrees. And because they're not at 90 degrees, they don't obey the rules of superposition, because they're produced by individual charged particles physically moving through the conductor, meaning every single one of trillions and trillions of electrons moving in the antenna each has its own field, and each of those particles produces its own effects on the local space-time that are not the same for the direction in front of it versus the direction behind it, depending on which way it's going. It's only at a certain distance that they become completely 90 degrees in relationship to each other, and they follow the rules of superposition, and therefore fall under Maxwellian electrodynamics and follow the Heaviside-Gibbs adaptations.
So one way that people, let me look for something that's like electric flow. We talk about polarity and flow, and a lot of the time we deal with positive and negative, right? But right. It has a lot to do with, again, that spin state being in a polarized relationship, in a monogamous relationship, a polar spin state. How is that similar or different, but in superluminous or luminous energy with dark energy? How is positive and negative similar and different between luminous and dark in terms of the way we metric these things? Are they complement? Are they involved with a relationship or a flow? What's the difference between them, really?
Well, let's say we could look at transmission lines as one of those examples where a transmission line just being the conductor, if we continue to increase the amount of current flowing through it, at some point it's going to start to travel much slower than it should. It'll almost bunch up on itself. So say a straight cable that's perfectly conductive, let's say a superconducting cable, well, electrons should be traveling through it at the speed of light. But if we start to pack way too much energy into that density, they're not going to be traveling at the speed of light. And even through a superconductor, we know that electrons do not travel at the speed of light. They travel slower than the speed of light. And the reason for that is there's other matter surrounding them. So if we can suck some energy out of the space in front of us, there's less physical restriction, less virtual matter that we have to go through. And now we can get these superluminal transmissions. I'm not sure if that really answered the question adequately, though. It's a rather tough one to kind of find an analogy for, because there's not a lot of other things other than electrodynamics that we have to relate back to the physical matter world to explain these concepts in a visualizable way. In fact, I wish I was better at graphics on computer, because I would very much like to create some animations to demonstrate some of these principles where we can see what happens to space-time if we remove a certain amount of electromagnetic energy density in front of us, and how it would change the way that light will propagate.
Dark flow is starting to seem kind of interesting as well, and I can kind of correlate why they're talking about dark fluid. But I think it's an interesting idea, dark flow. Then, if there's some sort of energy channel or flow, or if there's a more natural way that energy dissipates. We look at how lightning strikes, right? And lightning finds the easiest way to flow in a similar sense that water finds a similar flow. Lightning finds a similar flow. Do you think that there's something to that? I guess Nikola Tesla spent a lot of time focusing on energy flow. What do you think we can surmise about energy flow?
One example that I can give to speak on dark flow, even though I don't know much, I don't know officially what dark flow all entails.
Right, of course.
What I do know is if you have any matter moving in a certain direction, matter that is behind it will want to fall into the place where it just left. So we would think that electrons, all being the same charge, negatively charged, will just repel each other. And if we do try to cram a bunch of electrons into the same space and they're not moving, they'll repel each other. But a funny thing happens when we accelerate a bunch of electrons and try to send them along the same path. Instead of flying apart from each other, they'll form a beam. And the interesting thing is, why? Well, the thing is, electrons create something called a wake field, where they leave a hole in space behind them where they've just moved out of, that makes it easier for another electron to move into that space, because an electron behind one that's already just moved forward will see that electron as having a positive charge. And that sounds weird, but it'll actually see that space as being slightly more positive, so it will want to fall in and follow along. And they'll all want to line up and space each other out, and they'll actually form into a tighter and tighter beam the faster they're going. It's just one of those really strange phenomena. So dark flow is what it seems, what it seems that we're looking at here, talking about these sort of major currents on an astronomical scale. I think it could be explained by that same phenomenon, where if we accelerate any amount of mass, whether it's positive, negative, neutral, or whatever, or antimatter of the same, anytime we accelerate something along one axis, we're going to leave a wake field behind it that's going to create a better opportunity for things to fall into that space where stuff just moved out of. I know that it's going to be a bunch of terms that are probably way outside the proper audience, and that I really didn't cater adequately to your audience, but
this is perfect. This is exactly
something that people can reference later.
Right.
And if they want to really look into it, we've got a lot of engineerable things for space-time metric engineering that we can do something tangible with. And this is really where I want to go to. The last thing I'll say is we need to do experiments. All the theories, I don't give a damn about them. All the mathematics, I only give a damn about them so much as they apply to the lab bench. But ultimately, the most important thing that we can do is test out the crazy hypotheses and actually put them on the lab bench and see how they perform. And if we can't do that, then, well, we're just chasing our own tails and talking BS. And so even though a lot of the stuff I said today still requires a lot more experimentation, I have done quite a few experiments, and what I told you today is based off what my personal observations have been in the lab and what I know about particle physics and what I know about electrodynamics and what I've learned about, well, long since abandoned ideas of the aether. So it's going to be a highly controversial topic. Academics will not look at this and look at me and say, oh, this guy's definitely got his in order. But for the people that are really curious and want to modify gravity and don't think that Star Trek is a sci-fi fantasy, but it's quite an engineerable possibility, I hope that this acts as maybe a catalyst for us to look into this more and think we should be really concentrating on what we can do, because these phenomena are real and we've seen them.
I love
So
it.
with that, I've got to let you go, man. I'm sorry.
Not at all. It's awesome. We're going to look into the lack of the vacuum and what's really there. Thank you so much for being here, Jeremiah. Take care.
Hey, everybody, tune in to Recent Tarkarians.
Recent Tarkarians. Recent Tarkarians.